Talking through this tips and trips webinar. I'm going to do a little bit of introduction and then kind of introduce the tool a little bit, and then we'll go through some basic tips and tricks and things like that. So I guess we'll go ahead and get started here. So EMA Design Automation is a company that's basically a Cadence channel partner, reselling mostly the OrCAD product line from Cadence. We do sell some of the Allegro stuff as well. And we also have some of our own tools. We're more or less exclusive resellers for Cadence products in North America. We also carry the Autodesk line and a couple of our own tools, Timing Designer, Circuit Space, a few others that basically complement the Cadence agenda there. Here's just kind of a breakdown of some of the variety of tools we offer, basically the analog and mixed signal design solutions where you're seeing PSpice today, the FPGA design solutions as well. We carry the ALDEC tool set, Timing Designer for static timing analysis, FPGA system planner, PCB design solutions, a fairly broad variety of products for your design needs, basically. Okay, let's move into the agenda here. Basically what I'm going to do is come in and highlight features of PSpice that basically give you some increased productivity and simulation tricks, things like that. I'm going to show some of the most common solutions to user questions that we get, or some of the more common questions, I should say. And then I'm going to introduce an advanced package that you can add on to PSpice, which basically gives you kind of a broader realm of support for PSpice, where it can take you into different areas of analysis. And then, of course, show some further access to further information and whatnot. So I believe right now I'm going to do a poll question. So Kelly, if you put that up. So this is a poll question. Let's see if I can see it here. Basically, what we want to, we're just concerned with your biggest simulation challenges. So if you'd be kind enough to respond to that here in a second, and at that point we'll move on. I guess Kelly, let me know when that's complete enough so I can continue on without overlapping anything here.
Okay, Jerry.
All right. So now we're going to move on to just kind of introduce what PSpice is. So basically, simulation allows a lot of I guess it allows you to determine functionality and catch errors and whatnot in advance enough so that you don't have already committed to creating prototype boards and actually full production runs and things like that. It gives you the testing functionality via software, so it gives you very fast results on platforms that basically allows you to test corner cases and things that you can reproduce in the lab. It allows quick what-if analysis, and basically is designed to give you confidence in your design correctness and manufacturability. So that's the main purpose of what the simulation world affords to you. PSpice AD provides a complete simulation environment where you can actually do full analog simulation as well as digital, and you can even mix the two in there. So it gives you it's highly integrated with OrCAD. As you can see here, it's basically an OrCAD schematic that you use PSpice models for, and then in the simulation process, it gives you a nice waveform analysis result and various other output formats that you can use for this. PSpice is based on an industry standard SPICE simulator, the very one that was developed at Berkeley. We have huge model support, includes over 30,000 model parts for it. A large base of vendor-supported models there. A lot of vendors create PSpice libraries and PSpice models for the components and make them readily available. We have advancements beyond typical simulation to give you into optimization, manufacturability, component breakdown, those types of things. We'll be talking about that later as an advanced analysis package. And like I said, it's tightly integrated with OrCAD, so it's very intuitive in creating schematic flow there. We can. It also allows you to explore circuit behavior, DC to AC noise transients and whatnot. Allows you to look at those very discreetly. You can view node voltages, pin currents, a lot of variety in there where you can come in and look at specific parameters of your design. And I think there's actually another question we want to ask everyone. So we'll go ahead and pause for our second poll question here.
Okay, Jerry, we're all set.
All right. Just to continue on with the introduction here, like I said, you can do mixed signal analysis as well. So you can do digital coupled with the analog results. It gives you a nice mixed analog-digital simulation display, and basically allowing you to look at everything on the same axis and determine what types of transients you might have involved in the analog portion of your circuit. It can also be adapted for PCB, or it's mostly adapted for PCB design, I should say, but it can also be used for IC design as well. It's a long history of success in this, lots of model support for it. Basically brings the ease of use of PSpice into a more portable type of IC design situation. Okay, now let's move into simulation tips and tricks. And this is basically just some things that you may be able to help in productivity for moving your design along a little faster. First thing is you're able to copy waveforms to documents very easily. So basically, it's as easy as doing a copy to clipboard and then pasting into a document. So for instance, I have a simulation here that I've already done, basically just an RF amplifier or basically just a simple sine wave amplifier. What I can do in here is basically come in, go to the window, pull down, select copy to clipboard. You'll be prompted for the background and whatnot, how you want it to appear. By default, it just uses a black background, or I'm sorry, a white background for copy to paste. And then you can just simply do a Control-V or a paste into a Word document or something like that. So, or any other documentation that you're using. So it's very easy to do that cut and paste process. You can do the same type of thing with data tablature. So for instance, if you're doing a sweep, or if you just want to basically get a plotted XY plot table of what's going on in the waveform window, you can do that as well, and that's real easily done. Also, is simply just select on the waveform itself or down on the waveform name down here. Do a copy to clipboard here, and that puts the data onto a clipboard, and then you're available basically to go in and just do a Control-V into some editor or a paste editor, and it will basically come in and copy in the XY format your tabulated data. And I've got a little demo that I'm going to show here in a minute also on how to use this data to, for instance, if you want to use a particular waveform that you accumulated beforehand, if you want to use it downstream in another circuit, you can easily bring that waveform characteristic in. Okay, another thing that's kind of handy to know is there's not necessarily what you are used to in terms of saving a project as under a different name. If you want to do like a copy your project somewhere and make edits to it and still retain like a golden copy, whatnot, you can do this typically through a new as approach. And basically what you're doing is you start a new project and you base it on an existing project. And what that basically does is the same thing under the hood is what a save as would do. It basically creates the new project and then copies your reference project in there as it was from the last time you edited it, and then you can go in and make edits, and it's a completely separate project at this point. So that's kind of a little bit different twist on things when you're doing saves and copies and trying to do that type of thing, trying to replicate designs basically. Another thing that's handy is when you, say for instance, you want to archive a project away, so you're finished with it and just want to document it, or maybe you're having some simulation issues that you want to get help on from Cadence support or EMA support. The thing to do here is to archive the project. And the way to do that is very quickly, what you can do is you basically go to your design, your project page, and you select your design, your DSM file. And then once you select that, you'll see the archive project come available in the file pull down. So you can select that. It'll give you a window message allowing you to do some selections, whether you want to save library files, output files, where you want to put it. And then it zips everything up into a convenient little zip file, and then you can go off and email that or archive it away on a server or however you want. So that's very convenient for archiving and taking a look at things. Okay, there's a stimulus editor associated with the tool as well, and so like I said, what this allows you to do is create some unique stimulus rather than trying to more or less try to get an output from a circuit that has some kind of unique characteristic waveform shaping capability or something. You can actually just create that waveform shape you're looking for in the stimulus editor. It's available for things such as exponential functions, typical sine waves, trapezoids, square waves, most all common things that common waveforms that you're associated with. And it also allows you to do piecewise linear types of things. So you can actually create some kind of unique noise structure or something like that in a waveform and create that in the stimulus generator, and that will essentially allow you to then go on and treat that as a voltage source in your design. Kind of coupled closely to that is being able to stimulate a file or stimulate a circuit from a file. So I showed you before, flip back to that. What I'm going to do is go to this little schematic test here. So for instance, here is a circuit that I've set up as just a simple RC charging circuit. I originally simulated this circuit using just a straightforward voltage source, and what that basically did was give me just the RC charging characteristic of that particular capacitor. And then what I did after that is I came in and, as I showed you before, I went to the results and selected the waveform and did a copy to clipboard and then created a file from that waveform. And now I'm going to re-stimulate that circuit with the original RC curvature so that the RC charging response now will have a little bit different kind of a slower RC curve and whatnot. So you can, this is just an example of how you can actually drive a circuit with a new waveform file. So you find this particular source. This is a V-pulse or V-pulse piecewise linear file. That's the component that I'm using. And basically you put that in to drive your circuit and then essentially just create this link. It'll include a parameter link to link to the actual text file that you're going to stimulate it from. And so essentially that's what I've done here. This is the file that I've created before. This is what it's actually going to run it. And so at that point, you can simply come in, assign the new voltage source, and then run the simulation. So if I just run that right quick, it'll come up and give me basically the original charging curve is this right here, which is what I stored to a file, and then now that file stimulating the circuit gives me this new RC curve characteristic. There's also analog behavioral models, similar to the concept of driving a circuit with some unique waveform that's not necessarily something you get right out of a standard source. You can create the functionality that a particular circuit will basically be designed to do. Create that functionality in like a mathematical formula. So you do this with analog behavioral models. There's a variety of these models available. For instance, basic math, where you can just put together adders, subtractors. These are handy for when you need certain functionality of a design to stimulate the design you're working on, for instance. And you need this kind of stimulus to test and simulate your circuit. It allows you to get these types of stimulus into the circuitry quickly to where you can then work on whatever downstream effects that your circuit's going to have on these types of functions. Like I said, it's a lot of variety that we offer, voltage and gain control, frequency shaping stuff, where you can do filtering, low pass, high pass, band rejection, things like that. And you can also do some of the more complex math functions, differentiating, integrating, those types of things. So a lot of ABM capability, lots of models available to choose from. So just as a simple slide example of what you might want to do with this, you want to try to create some kind of voltage controlled resistor. You can do that with a voltage source, basically an ABM that would emulate that. So this circuit right here basically gives you the characteristic response you're looking for, and then here is that characteristic response implemented into a circuit using an ABM. So you simply just put that in as a part, and set the mathematical formula for what it's going to respond to, and then you're really set. You're good to go in that. You can step that up to some more complex functionality. So, for instance, if you want to do a voltage-controlled oscillator, that's very easily done here. You can see the signal there, the actual formula here as a sine wave, and based on a control input stimulus, that frequency is altered based on the input. Same with phase lock loops. Sometimes it's very complex to construct. If you just need a phase lock loop to kind of respond to or stimulate a circuit, you can certainly create it very quickly with ABMs. Okay, another concept is when you have a design and you want to do different types of simulations on a particular circuit, you can step through several types of things, of transient analysis and AC analysis, DC analysis, all these types of simulation capabilities. One of the things you may not know is you can set up various simulation profiles, multiple simulation profiles on the same circuit. So one could correspond to a transient response, another could correspond to an AC response, where you're doing a frequency response or something like that. It's very simple. Just create another simulation profile, and that affords you the ability to go in and simulate the same circuit with just a different simulation characteristic. It saves you from having to recreate things and keep things more isolated and like a separate circuits or separate designs. Same concept also here, but in this case what you could do is you can have different schematics in the same design file and toggle with them using the profiles. So in this case what you would want to do is come in and create another schematic folder, and basically you would do that with just a right click on the design file, select new schematic, and it will come in and put down a new schematic folder, and then you can either create the schematic or move a schematic into that second folder to isolate them, and basically these are two separate simulation environments, so to speak, within the same design. The simulation profiles are kept separate because they're assigned to each basically each folder name for each of the schematics. So, for instance, to get one to have dominance over the other, so in other words, you want to run this first schematic. You would basically make that the root for the PSpice simulator, and then it would run everything corresponding to that particular simulation profile. Or you could just select that simulation profile and it automatically makes that particular design the root design for the simulation. Another thing that's convenient is the ability to do parametric sweeps. So, for instance, if you want to do some kind of sweep response, in this simple case, I'll do basically an evaluation of the simple RC circuit I showed you before. But basically, you can sweep a variable, and how you do this is essentially assign a variable to the component as opposed to the actual value of that component. And you have to use the curly braces here to identify that it's a variable to use. So you assign that into the value field, and then you can create a parameter block from the special function. This is basically just a parts library that has a param block in it, and then create that variable in the parameter block, assign it to a value, and then if you don't sweep it, it'll basically just use that parameter block to reference that particular value for that component. And then this also affords the ability to come in and do a sweep and I'll just show you how quickly and easily that's done right now. So here I've already got this set up to where I've got just a simple RC circuit. It doesn't matter what I'm stimulating this with at this point. Here I've assigned that a variable called cap value, and so cap value right now is set to 1 nanoseconds by this parameter block. So this is controlling the value of that capacitor. If I go in now and take a look at my simulation profile, right now I'm just doing a general setting here, so it just runs just like you saw a while ago. It'll run out to 10 microseconds. If I want to come in and do a sweep, I'm going to set this up a little further so we can see, so it'll run a little longer. And then what you want to do is come in and select parametric sweep. And then in this case, I've kind of already set this up just for the speed of the webinar here. So I've set this, you can select to sweep a global parameter. You can also sweep a source, a model parameter, temperature, things like that. But in this case, we're just going to do a global parameter. It was identified in the parameter block as cap val, and so that's the parameter it's going to sweep through. Here you can select either logarithmic or linear. In this case, I'm just doing linear. I'm going to start at 1 nanoseconds, end at 20, or nanofarads rather, end at 25 nanofarads with 1 nanofarad steps. So once I set this up, just select OK to store that in the profile, and then just run it right quick. What it's going to do is come up and prompt you that it's about to run all of these particular sweeps and basically start to plot them. And in that case, you just select OK, and then it plots everything in the probe window for you. You can also take this a step further. I think the next slide basically is going to show you this, but just while we're sitting here, I might as well just show you as well. You can do things with sweeps like this, like performance analysis. So if you want to do some things here, for instance, if you want to see what the linear or what the response and rise time is based on capacitance, capacitance changes, you can go through this. Here I'm just going to select a rise time parameter in the performance analysis. And in this case, I'm going to select my output parameter of V out of the schematic. Once I select OK, then at this point I'm ready. I could step through or just finish it out. And this is basically giving me a plot of rise time over this sweep period as a performance analysis capability. So you can do some more advanced stuff with your parametric sweeps. And that's basically what this slide was referring to, the ability to do these types of plots to give you some kind of unique perspective on the sweeping that you're doing here. Okay, let's move into some simulation troubleshooting. Those are mainly some tips and tricks that you may or may not be aware of that kind of gives you some advances into how to more quickly get through setting up and executing your design. So some of the troubleshooting you may run into are these things. So first of all, reading the output file. So in this case, what you've got is a particular simulation that you ran, and there's some kind of error associated with it. And usually what you'll see is basically the output file associated with that. And what it typically does is runs these dash lines underneath the problem line that it had as basically identifier that essentially locates where in the file the problem is, and a little dollar sign indicates the parameter problem that it had, or at least the line item it had a problem with. And in this case, it happens to be a parameter issue that there's a space between the numeric value and the actual parameter unit, and so it's basically flagging that as a misread on that particular line. So that's kind of how that is set up. The output file goes in and tries its best to flag where it has an issue with it. Floating nodes. This is a common problem. PSpice has to have its ground source named with 0. So rather than having a ground symbol with the name G and D, you've got to have something you've got to have a name 0 associated with that. That's really the only way PSpice understands how to get your common return point for the PSpice sim flow. So this is fairly common. You'll get these types of errors associated with it floating. A particular node is floating or something like that, and it basically means it can't get back to its, it can't make a closed loop back to its origination sim point. Another common simulation issue is basically when you have two capacitors in series like this, components like capacitors and inductors and whatnot, they're basically ideal components. And so what they do is they tend to not allow any DC to pass through. So when you have a situation like this, it's easily resolved just putting a high value of parallel resistance in this particular circuit to actually provide some type of DC path through there, and that will basically alleviate the issue of having this particular center node that's in between these being isolated and floating. So as long as just make sure it's a large enough resistor and it won't affect the performance of your circuit. Same type of situation with parallel inductors or dual parallel voltage sources. Again, it's considered an ideal source here, so to make it less ideal, just put a series resistor in these situations. That provides, basically breaks a loop and provides more complete simulation issue. Okay, sub-circuit undefined. This is probably outside of the isolated ground and whatnot. This is probably the most common error that we see. And it basically has to do with the simulator not having the configuration for the library location. So when you do things like download a vendor the library is included with the installation. So that's how it easily finds all of the installations. Download a model to use, you've got to point to where you're storing that live file so the simulator knows how to make that model react in the circuit. So it's basically just an issue of going to your simulation profile, go to the configuration tabs, select library as a category, and then you can just browse to the place on your machine or server where these library files exist. Another issue is sometimes schematics can be mixed with either PSpice components and just standard ORCAD symbol components that have no underlying PSpice model. And this is the type of error that you'll get when that type of thing happens. You'll see less than 2 connections at a particular node, meaning this node here has a PSpice connection on the resistor, but this particular inverter gate here is not doesn't have any type of PSpice model associated with it. So this node, according to the PSpice simulator, is just out here floating. So that's where you see basically that type of issue is when you're using non-PSpice parts. To resolve that, just make sure the parts that you're assembling your schematic come from the library PSpice location in your installation. So it'll be under Tools, Capture, Library, PSpice. Debugging and convergence, it's always an issue sometimes to go through and make sure that your simulation and debug times give you the maximum efficiency. Sometimes you'll have circuitry that simulates a long time and parts of those simulations is really uninteresting data. You want to get to a certain point in that simulation where you're more interested in analyzing. So there's several capabilities in the tools to take care of that. Also, when a simulation won't converge, meaning it can't get to a solution, there's also some things to help you with that as well. One of those things for speeding up a simulation and getting to a particular interesting part of the simulation that you want to deal with is to schedule your tolerances. So you can also schedule your time steps, but it's the same corresponding capability. Set a schedule parameter in any of these tolerance values, and that will basically give the ability to zip through an uninteresting part of a simulation, focus more slowly, more detailed, step with finer granularity on a area that you're really interested in, and then zip back out to the end of the simulation. So you can do all kinds of scheduling and whatnot to take care of this type of thing to get more efficient run. Checkpoint restart is an idea that allows you to kind of manage charge-up cycles. Sometimes simulation can take a long time. A large portion of that time is any charge-up type cycle. So what you can do is use the checkpoint restart capability to simulate one time to take note of the charge-up cycles of the particular circuit and then store those off and then restart the simulation when you make a small change. You can restart that simulation at that point, at the, I guess, stable point of your charge-up cycle. So to do this, for instance, here's an example of what you might want to do with this. Here we have just a simple RC circuit again where you've got a charge-up cycle. This charge-up cycle, the characteristics not really going to change that much. So what you can do is run this one time and then save this off as a basically your base run, and then do a checkpoint restart. When you, for instance, you want to change this particular R2 resistor from 1K to 2K to see how that affects the circuit, and then you can restart. You can avoid all this initial charge-up portion and just start from a particular time spot in the previous sim and take off from there. So there's one example where you want to do it. Maybe you want to do it again from a different point. You can do that again, changing a value and see what happens to your simulation. So this is very nice and convenient in the sense that you can save this stuff off and not have to re-simulate a lot of kind of redundant charge-up cycles in this particular case. To save checkpoints, you simply go in your simulation settings and analysis and select the Save Checkpoints box, and then provide the details in here of where you're wanting to save that information. And then to load a checkpoint from restart, you go in and your simulation profile, check Restart Simulation under Analysis tab, and then give the name or the time point at which you want to start from. Another thing you can do is, if you want to identify errors quickly, having some issues, you can use a behavioral generator to basically stimulate the circuit and then stop at a particular point where you know at this, if, for instance, in this case, if the voltage exceeds 21 volts, you know that there's a problem and you just want to stop the simulation. So you can use behavioral models to do this. These kind of control give you an ability of control when you exceed a certain parameter in your design. You know the simulation's gone awry, you can stop that. And this is kind of a charted example of this particular design. Will run up to a 21 volt point. It'll hit that and stop and then give you this error printout. Auto-convergence. So if you're running a design that has, maybe it has some particular issues where it has some spikes in it or something like that, sometimes these things can present problems to the simulator where it can't, basically the step size it's using or something can't necessarily get the simulation to actually converge to a solution. When that happens, you typically get this error window here when it's a convergence error. And at this point, you can come in and either do some manual attempts at relaxing some tolerances to try to achieve convergence. But the problem with that is you may not know which one to adjust that well. You know, you're not real sure where the problem actually exists to go in and provide a solution for it. So auto-convergence helps you to do this. What it basically does is it gives you, it actively controls all of these tolerances itself. It only takes up as much tolerance space as it needs. So it'll go in and do all this work itself and allow you to converge to a solution. So it's basically letting the simulator make these decisions to achieve convergence. And 9 times out of 10, this works pretty well. It'll go through. If it hits a problem where it can't converge, as long as restart selected, it'll try to relax any of these limits and then restart to try to achieve that result for you. And then once it's done, it tells you what it changed, basically what it optimized to achieve that convergence. Okay, so that's some of the simulation issues. Now we're going to talk about an add-on to the product. So there's a couple of add-on things that you could do. One is Simulink. This is a add-on issue or add-on product that you can add on to PSpice to integrate with the Simulink mathematical simulator. So what this allows you to do is put into your mathematical circuit setup in Simulink a link out to a PSpice circuit. So for instance, these things can co-simulate. You know, when it needs simulation responses from PSpice, it will go out, stop its simulation, go out and run this simulation to get the results out of the PSpice circuit, and then come back, handshake back into the MathWorks simulator and continue on at that point. So it gives you a level of co-simulation in a mathematical simulator like that. It's really convenient because it gives you the ability for to account for reflections in circuits and kind of a better way to deal with models that are ideal in Simulink. Gives you more of a realistic type of modeling capability in that particular environment. Another package you can get is the Advanced Analysis package. And basically what this does is it extends the capabilities of PSpice into additional analysis fields. So for instance, you want to do things like maximize design performance, your yield, how hard am I stressing my devices, things like that. This Advanced Analysis package allows you to expand into that area and take a look at some of that type of analysis. There's 5 tools associated with Advanced Analysis package. Smoke is the first one I'll show you here. It basically detects component stress. How hard am I driving these? Am I pushing, for instance, a VCE on a transistor? Am I pushing that voltage too hard, or is it too close to its maximum settings? There's a sensitivity tool that basically gives you an idea of which circuits affect your component parameterization the most, and I'll show you that. Optimizer basically allows you, if you're trying to, you set up a circuit to achieve a certain set of parameters as an end result, and you're close, but you want to fine-tune it a little bit. You're not really sure where to go to attack that. To let's say you want to narrow your bandwidth or something. The optimizer gives you an idea of basically it'll do that for you. It'll go in and change tolerances, change values to try to achieve a result that's more close to the parameters that you specify. There's Monte Carlo analysis, and this basically analyzes statistical behavior of your circuit to give you kind of a sense of what kind of yield you're going to get out of the circuitry. It's based on component tolerances that you use, and it goes through and alters these tolerances and gives you an idea of how many of these circuits are actually, given the tolerances you're using, how many of these circuits are actually going to meet your end parameter results. And the final is a parametric plotter, where you can sweep any number of design elements against each other to try to achieve a certain particular design goal. Let's go ahead and look at smoke. So I'm going to introduce it here in a slide and then just jump to a circuit and just kind of show you how this works. So basically the smoke tool gives you an idea of stress analysis for your circuit. So basically you can set up different derating values, and basically what this means is you can dictate or control how hard, or basically where these limits are of where you want to drive the parameters of your circuit. And it'll go off and basically run the simulation and then give you an idea of where your stress points are. So let's go ahead and set that up here. I've already, I'm going to go ahead and close these particular projects and just start with a different one, which basically gives me the ability to go in and show this advanced analysis more conveniently. So what I got here is an RF amplifier, and I've got it again set up using a parameter block. You can see here that basically most all of the tolerances I want to look at, or the I have it set up as tolerances and smoke limits. Smoke limits are things like maximum resistance, maximum temperature, things like that. So you can kind of see how these parameters are set up. The way you actually control these, basically, for instance, in a passive device, you have, if I double-click on the resistor and just open up the properties field, it's over in the center of the screen here, you can see I've got some of these set up to basically reference the parameter settings in the parameter block, like my negative tolerance is set by RTOL, positive tolerance, temperature effects, things like that. All of these things are set up via the parameters block, so therefore they're easily controlled in this area. An active component you would basically have to set up in the PSpice model editor. So here you would edit the model. It's basically going to bring up the model editor. And then once it loads up here, the model editor presents basically, in this particular case, it's a transistor. So it presents you with a table of simulation variables to control the model. But it also gives you a smoke folder. Now, this smoke folder is present in any of the components that are provided with PSpice. And then you have the ability to create that if you're creating new components and bring in vendor parts and stuff like that. You can save these and set these up to your liking. So in this case, with this particular thing, we're going to pay attention to the VCE here, because that's really where we're going to focus on this particular demonstration. We're going to take a look at the collector emitter voltage on this particular transistor. Its absolute maximum ratings are what's listed in smoke. And then, like I said, you can derate these. For instance, if you don't want to drive all the way to 12 volts, you can derate this a little bit. So we'll go ahead and take a look at how that's done. Okay, so I'm going to do an AC analysis first on this, so I have to run a baseline simulation. So we'll just go ahead and run with that. So I got some noise parameters basically here plotted. But what you'll notice here, and these will come into effect here in a minute. So basically we'll put this down as a base simulation, and then what I want to do is go launch the smoke tool. So I can come over here back to my PSpice Advanced Analysis tab, and you can see all the tools that are available here in the Advanced Analysis package. I'm going to launch the smoke tool, and now it's going to prompt me for what particular license I want to use for that. So I select that, and now it's going to come up and just run the smoke analysis against that particular simulation. And so what you can see over here, this is the actual, how the percentage of how close I am to those maximum ratings, those maximum smoke values here. Each one of these values can be assigned to either an average type or a peak type. In this case, I'm just going to hide it. Some are invalid here because I haven't, they're not filled out completely, or they don't apply. So I'm just going to turn off the invalid ones, so you can just be interested in the ones that the ones that make sense here. So in this case, I'm driving pretty much everything at 100% of rating, so I'm just looking at how close I am to the absolute maximum defaults for these components. Say, for instance, I want to go back and say, okay, I don't want to drive these components that hard. I want to come off my maximum values and only drive everything 75% or something like that. The way you would do that is basically just select a new derating table, and you can actually customize the derating table, make your own. I've got a standard one in here that kind of reduces the derating numbers for these parts a little bit. So I selected my standard, and now I'll just redo the simulation. And you can see the derating values have changed now. So I'm only driving the VCE parameter, for instance, at 50%, which means that for a maximum peak rated value, it's going to flag an error if anything is over 6 volts. So in this case, my measured value for the simulation is 8.1. That is indeed over 6, so it's telling me how much I'm exceeding that particular parameter by 136% there. So it gives you an idea of how hard you're driving these parts, and you can even back off of certain absolute maximum ratings if you want to pad in, you want to design in like a margin of safety there for things. Okay. So let's jump back to this right here before we go into the sensitivity tool. One of the things the sensitivity tool does, well, I guess first of all I'll kind of introduce it a little better here. So this is the so sensitivity basically gives you an idea of which components are actually the most sensitive to your output parameters, and the remaining tools in the advanced analysis all operate basically on measurement assignment. So you have to basically establish a measurement that it's going to do the sensitivity analysis against. So in this particular flow, what it's going to do is go and look at each one of these 4 assigned measurements, and then basically give me a sensitivity analysis as to which components would affect this particular output characteristic or this measurement the most. So if I jump back over to my simulation here, I've already got my measurements set up for smoke analysis or for sensitivity analysis. So it's really easy to set these things up. What I'm looking at right now is maximum dB out on the V load here, a bandwidth parameter measurement, and a few noise measurements as well. And so it's easy to add new ones. Just click on this bar. You can come over and look at some macros that are already established, which I am using some of these as well in here. Or you can just look at just pure output variables and assign something yourself there. But that's how you add the measurements, and that's what smoke essentially runs on, is those types of analysis measurements there. So now we'll go ahead and, again, since I've already got this up, we'll jump over to the sensitivity. And so you'll see that these measurements were transferred into the sensitivity tool. You'll see the components listed there for this particular design circuit. And so now if I just go up, we're already set up to go. If I just go up and run the sensitivity tool, it's going to go through and zip through 14, since there's 14 components listed here in this design, it's going to zip through 14 sensitivity runs, and then it's going to do a worst case analysis, a min-max type of thing. So you'll see that done. It's completed now. And so what comes up here as it looks like component R9 is the most sensitive component to my maximum dB output on my load. You'll see that the original simulation had it at roughly 9.41 volts. By varying tolerances and whatnot, the minimum that you could get out of that is 7.3, and the maximum for that measurement was 11.3. So you see kind of statistics accumulate down here for your specifications. The actual sensitivity is listed up top. So you'll see it's sorted on the one that has the most sensitivity, the component that's most sensitive to the output parameters of the circuit. And you can read this as for every % change in R9, you get a maximum relative sensitivity here of for instance, a 99% change in the output. So for instance here, the original setting for R9 was 50 ohms. It's a 10% tolerance, so you'll see a minimum 45, maximum 55 for that particular device, which gives you a relative sensitivity of about 44.5 millivolts here for that particular component adjustment. So that is the one component that affects it the most, and then they'll descend down upon which component is next in line to give you the most effect. And you'll see these change as you select your different measurement results here. The component values change. So for instance, bandwidth R4 is the most sensitive that affects the circuitry like that. Okay, so now let's look at Optimizer. So the Optimizer tool, what it allows you to do is come in and say you want to take a look at parameters of your circuit, and you're close to what you want, but you don't quite have, you want to hone it, fine-tune it just a little bit to try to, say you want to narrow your bandwidth a little bit or drop your gain just a little bit, or something like that. Obviously, one of the ways you can do it is go in and just try to start figuring out which one of the components yourself that you want to optimize to try to achieve that. But the nice thing about the advanced analysis package is number one, you can use this tool in conjunction with the sensitivity tool to find out which one of the components has the most effect on what you're trying to achieve. And then you can list those components over here as the parameters for this particular tool to go and fluctuate. And so what it'll do is you list components interested in controlling. The tool will go through the simulation and vary these values of each one of these components a little bit, and to try to determine how close it can get into, how close it can come to meet these performance parameters that you're trying to hit. So in this case, I've jumped to the Optimizer tool. Based on that same base simulation, I'm going to go ahead and run the simulator. And so in this case, it's going to run through quickly to try to optimize this. And while this is running, I'll kind of explain what I did. So you'll see that the measurement parameters are brought in as well from the measurement setup in the simulation window. What I wanted the tool to try to achieve is to try to get a maximum dB, a minimum dB of 5 and a maximum of 5.5. So I wanted it to try to hone in a little bit to try to adjust that just a touch so I can get within this range. For bandwidth, I wanted to try to get a minimum bandwidth of 200 meg. So 200 megahertz there. Originally it was 150, so I wanted to try to bump that up a little bit to try to achieve the results. And I did the same thing. I wanted to try to maximize some of the noise figures here, maximum of 5 and a maximum of 3 on this one. So I set those up here, and then when I ran the tool, it comes back and reports originally what those values were, and then if it once it converges on an error, it comes back and shows me what it was able to do by varying these 3 components. So in this case, I got a maximum output of 5.2 volts. I achieved my 200 megahertz minimum goal of bandwidth. It's a 212 roughly. So you can see my percent error, 0% error, meaning I've hit the goals that I wanted to hit. And this is what it did to achieve that. It came in and varied R8 from original value of 3.3 now to a minimum of 3 and a maximum of 3.6. That's the range it went through. It actually hit the value at 3.57. So that's the current value of R8 that would basically achieve the goals I was after here. Same thing with R6. It was originally at 470 as was R4. These two resistors were adjusted. The R6 value was adjusted to 702 and the R4 was 238. So that got me like almost dead on from what I wanted. Now the next thing to do is okay, these components, I can't really buy those very easily off the shelf. So I wanted to run one more time and give me a discrete association with those, a discrete value associated with those components. So I can go buy basically off-the-shelf components for this particular characteristic. So what I do is I set this up to run one more time using discrete component values, and then once I do that, it'll go and do one more run, and then give me an adjustment on these values, and come up and basically tell me what kind of standard values I can go off and get for these. So here it adjusted R8 3.6, and then R6 to a 680 and a 240, which are easily purchasable components. And in this case, you can also again check to see your parameters here. We're still in a 0% error here, so we're pretty much good to go with this particular optimization. Okay. You can also do curve fit. I'm not going to show you that today, just in the interest of time. But if you have a particular XY parameter set up that basically is a a curve plot, and you want a particular characteristic to try its best to meet that curve, you can certainly do that as well. You basically apply that parameter, have it read that particular XY plot, and associate what column is what axis, and it will go and basically do its best to try to achieve that fit in the same manner. Okay, back to the slides. So we talked about sensitivity, we talked about the optimizer. This is an example of what the curve fit will actually do for you. It'll come in, if you have a a golden curve, it'll come in and try to meet that particular response there. The other two tools, which I'm not really going to show just in the interest of time, is basically the Monte Carlo tool. There is a version of Monte Carlo in the basic PSpice, but this one takes a little bit further, allows you to do a little bit more capabilities with it. But basically you set it up such that it'll do a base run as before, and again you're doing these standard measurements that were brought in from the original PSpice run. So you can set this up, do a base run, and then switch to the Monte Carlo tool. And then it will basically what you do in Monte Carlo is it will show you a probability density graph of that particular result when you run it. And then once that's established, you can come in and basically move these cursors to where you would consider basically an effective result for that particular parameter for your end result in your circuit. So for instance, if you want maximum bandwidth, for instance, if you want to narrow this down, what you would do is set your cursor values. Here it's showing maximum dB, so I guess I'll just talk to that. If you want your maximum output to be 9 volts on a minimum and maybe no more than 10 volts, you want that type of range on your final circuitry. What the Monte Carlo allows you to do, once it does the probability density graph, you can move these cursors in and it will tell you basically what type of yield that you'll get out of these based on the circuit tolerances, the component tolerances you use. It will give you a percent of yield that will basically tell you how many, due to this probability graph in your component tolerances, how many circuits built with these components will actually fall into that particular range of 9 to 10 dB. So that's kind of nice to know in this particular case. You're going to have somewhere along the lines of a 70% yield, meaning that 30% of your boards will fall out of tolerance for that particular parameter. And then at that point, you might want to go back and use the sensitivity tool, the optimizer tool, to figure out how to tweak the circuit a little bit to give you a better yield, and you won't have to throw any boards away. Parametric plotter, like I mentioned before, allows you to actually do parameter sweeps on a multitude of components, and you can actually plot them against each other. So in reading the graph, once you set that up, say for instance you have two components that you want to vary. You want to vary both components a little bit. to try to meet a bandwidth perspective or something. So you go through, tell the tool that you want to alter one resistor, then alter the other resistor, and give it a range for how much possibly you want to get it in there, and how many steps. You got to be careful how many steps you set it, because what it'll do, for instance, 10 steps each will do 100 simulations. So you got to kind of be careful there using the parametric plotter, because it can, if you get a little carried away with the number of steps, it can run basically set up a lot of simulations and take up a lot of time. But that allows you basically to look at your plot and see what kind of values you want to choose for these two components to achieve a certain result. So if you're, say this line was a 200 megahertz bandwidth capability, and you wanted to just stay above that, you could grab, and one of your resistors, say, was a 10 ohm resistor, and that would be this line here. You could do this green curve to see what resistor that R2 was, for instance, to give you a value of those two resistor pairs to hone in on that particular parameter. Okay, that pretty much does it for most all of this webinar. Right now I'm going to show you some available resources that come with the tool. So in this area here, when you install the tool, there's user guides and reference guides. There's help files, a quick reference guide. They're all installed in your basically in your installation location for your tool set. And this kind of gives you a reference of where to find those and what the file names are. We'll send this full set out so you can actually see in references as you can find these particular devices. So I think we have a couple of more poll questions right quick, and then we'll close this out. So go ahead and do poll question number 3, which I think I'm a little bit late on, so I apologize for that. So Kelly, go ahead and put that up, please. Everybody done, Kelly?
Yep, I'm just going to switch it over. There's one final one. We're just interested in learning what you guys would like to see in a future webinar from EMA. If you don't mind voting one more time.
Yeah, this kind of gives us an idea of how to shape these webinars for the most efficient customer usage, things that customers really want to see. So it gives us a better idea of how to better support you.
Okay, thank you.
All right. So that concludes our webinar today. This is kind of our contact information. You can call technical support on our hotline or give us an email at techsupport@ema-eda.com. My contact information is at the bottom here. I work out of Austin, Texas, so I have a 512 area code there. Or you can just email me there, however you like to do it. And once again, this concludes the webinar, and I'd like to thank you for your time.